In this video, we're going to use R to illustrate the importance of interaction terms in models. So first, I'm going to use these 3 lines of code to read in the dataset. Turning off scientific notation, setting the working directory, and reading in taxi. Let's check the dimensions of taxi. Oh yeah, there's 453,000 observations in this dataset. Next, I'm going to identify the size of the sample set and store it in N, and then divide the data into training and test sets, dtrain and dtest. I could check the dimensions of dtrain and dtest if I like. Now, the first thing I want to do is just create a scatter plot of a relationship. I want to explain the cost of a ride, or the fare, with the tip amount. So can I predict how much a ride costs if I know how much the passenger tipped? Well, let's look at a plot of these things, tip and fare together. It's always going to take a minute to create a chart when the data set is this large. Okay, so every dot represents one ride in the taxi. On the horizontal axis, we identify the tip amount, and on the vertical axis, the fare amount. And you can see that in general, these two things tend to increase together, but there are lots of unusual outlier situations. Now, let's consider, instead of plotting all of these points in black and looking at them all together, what if we separate the rides where the passenger paid in credit and where they paid in cash? Let's just visualize what that would look like. So I'm going to use these 2 lines of code here to plot another scatter plot, and the first one separates out all the rides where the passenger paid with credit. Credit equals 1. And I'm going to plot those points in blue. In the second line of code, I'm using the points function, which is going to add dots to a scatter plot that already exists. And I'm going to add the credit equals 0 rides to that chart, and I'm going to add them in the color gray. So I'm going to create this plot, and we'll wait for it to appear. But in blue, we'll have the rides where someone paid in credit, and in gray, we'll have the rides where someone paid in cash. Now, you can see in blue, we have a very large number of rides. People often paid in credit. And in gray, we have all the cash rides, and those just do not seem as frequent. Now, the question I have for you to think about here is, should the same model explain the relationship between tip and fare for those rides that were paid for in credit and the rides that were paid for in cash? So does it look to you like the same line could be drawn through the gray dots to best represent that relationship, and through the blue dots to best represent that relationship? Well, it seems to me that here the middle of the gray dots might be looking like this, and the middle of the blue dots might have a different slope to it. So what I want to understand better is, what would those 2 lines look like if I did create separate lines? So I'm going to create 2 models. Fit1 is going to be a model for the blue dots, where people paid in credit, and Fit2 is going to be a model for the gray dots, where people did not pay in credit, they paid in cash. And if I want to print out the summary of Fit1 and the summary of Fit2, I could see that indeed tip is a significant predictor of fare. We've got our 3-star designation there. And now what I'd like to do is take those 2 models and add them to the chart so that we can see what model best represents the blue dots and what model best represents the gray dots. So I'm going to use the points function to add the predictions from Fit1 and Fit2 right onto that chart, in orange for the rides that were paid for in credit, and red for the rides that were not paid for in credit. So looking here at this chart, we see that the orange line goes through the blue dots. It best describes the wide variety of blue dots, all the rides that were paid for in credit. The red line is the best line that goes through the cash rides, the gray dots. And the two lines are really very different. They cross one another very obviously. They have very different slopes and very different intercepts. But if we were to look at all of these dots together and create a single model without separating by credit, then what we're really doing is saying there is no difference between the orange and red line. I'm accepting a single line through all of these points. So let's create that model, the one where we don't separate. We'll create Fit 3 that explains fares with tips with no consideration of credit whatsoever, and we'll plot the predictions in green. So you can see if we create a model that does not separate the two, the line will go directly through the middle of the two lines we just created separately. So the green line represents what would happen if we did not consider credit. The red line is the cash rides, the credit is the orange line, and the green kind of goes right through the middle, considering an average of cash and credit rides. What if we added credit to the model? What if we used tip and credit to explain fare? Would we do a good job? So let's add credit to the model, and we'll draw the model that is created in purple. We're going to plot the dots that are the predictions from this model with tip and credit on the same chart we've been using, and they'll be represented in a different color. So look here, what's happening is that there are two lines drawn in purple. They are parallel. So what we're saying is, if someone paid in credit, it will bump up that tip by a little bit. And if not, it'll be bumped down. So we have two parallel existences for the two different universes of paying in credit or paying in cash. And depending how you choose to pay, it will affect the prediction by some fixed distance between those two things. That's essentially the coefficient of credit. So all this time, we've really been drawing multiple lines by adding multiple variables. We're changing our prediction according to the existence of additional variables in the model. But it still doesn't solve our problem. It doesn't give us the red and orange lines. It covers up the orange line and then draws another one next to it. So what the interaction term will do is allow us to represent the orange and the red together at the same time. So let's create the interaction term. An interaction is a product of two variables. So we will multiply tip and credit together and create something that we're going to call TC int. Then we're going to create a model, and we'll look at the summary. I'll widen out our box here so we can see the model. We're going to create Fit 5 that adds tip, credit, and the interaction between the two to the model. Over here in the summary, it looks like tip is a significant predictor, credit is a significant predictor, and TC int, the interaction, is indeed a significant predictor. Now let's visualize what happens when we add that to the chart. The two black lines cross, and the tall line, the higher line on the right, that covers the orange line. It covers the line that goes through the blue dots. The shorter line down here at the bottom covers the original red line that went through the gray dots. So essentially, an interaction term is allowing us to draw two not parallel lines. We're changing the slope and the intercept and drawing two separate lines to represent this problem if we add an interaction term. So when we add an additional variable, we're drawing a second but parallel line, having the same slope but not the same intercept. When we add an interaction between two things, we're allowing both the intercept and the slope to vary, and we're making predictions for two different populations that are completely different lines.